If you have 12 circuits at approximately 10 amps each, you can add them for a total of 120 amps of load. Then divide by 3, assuming a completely balanced system on the 480 volts panel, resulting in a load of 40 amps on 480 volts. This calculation relies on a few key assumptions. Firstly, all 12 circuits are connected to the same 480 volts panel. Secondly, the system is completely balanced, which means the load is evenly distributed across all 3 phases. Thirdly, the current draw is the same on all 12 circuits. The total load calculation is as follows: 12 circuits multiplied by 10 amps per circuit equals 120 amps. The load per phase, assuming a balanced system, is 120 amps divided by 3 phases, which equals 40 amps. It is important to remember to verify the actual loads on all 12 circuits to ensure accuracy. If the system is not completely balanced, the load on each phase may vary. Furthermore, the generator's capacity should be checked to ensure it can handle the additional load. When working with electrical systems, accuracy is critical. The assumption that all circuits draw the same current and that the system is perfectly balanced is rarely true in real-world applications. Before making any modifications or adding loads, a thorough assessment of the existing system is necessary. To accurately determine the load on each circuit, use an ammeter to measure the current flowing through each one under normal operating conditions. Record these measurements for each of the 12 circuits. Once you have the actual current measurements for each circuit, sum them up to find the total current. For example, if the measurements are 9 amps, 11 amps, 8 amps, 10 amps, 9.5 amps, 10.5 amps, 11.2 amps, 8.8 amps, 9.1 amps, 10.9 amps, 9.7 amps, and 10.3 amps, the total current would be the sum of these values. To calculate the load per phase, you need to consider how these circuits are distributed across the 3 phases of the 480 volts panel. Ideally, an electrical system is designed to distribute the load evenly across all phases to minimize imbalance. An unbalanced system can lead to inefficiencies, overheating, and potential damage to equipment. To determine the load on each phase, identify which circuits are connected to each phase. Sum the current measurements for the circuits connected to each individual phase. For instance, phase A might have circuits drawing 9 amps, 10.5 amps, 9.1 amps, and 9.7 amps. Phase B might have circuits drawing 11 amps, 11.2 amps, 10.9 amps. Phase C might have circuits drawing 8 amps, 9.5 amps, 8.8 amps, 10.3 amps. Calculate the total current for each phase. If the totals are significantly different, then the system is unbalanced. After calculating the current on each phase, calculate the apparent power for each phase using the following formula: apparent power in volt-amps equals voltage multiplied by current. In this case, the voltage is 480 volts. So, apparent power for phase A equals 480 volts multiplied by the total current of phase A. Repeat this calculation for phases B and C. After calculating the apparent power for each phase, you can calculate the total apparent power for all 3 phases by summing the apparent power of each individual phase. To convert apparent power in volt-amps to kilowatts, divide the total apparent power by 1000. Kilowatts is a more commonly used unit for expressing the total power consumption. The generator's capacity is a critical factor to consider. The generator has a maximum power output rating typically expressed in kilowatts per kilovolt amps. Make sure that the total calculated load, including the existing loads and the proposed additional loads, does not exceed the generator's capacity. It is also important to consider a safety margin. It is generally recommended to keep the load and the generator below 80% of its maximum capacity to ensure reliable operation and prevent overloading. To determine the existing load in the generator, you need to gather information about all the loads currently connected to the generator, including lighting, HVAC systems, motors, and other equipment. Obtain the power consumption data for each load, either from nameplate ratings or by measuring the actual current draw. Sum up the power consumption of all existing loads to determine the total existing load in the generator. To determine the additional load that can be added, subtract the total existing load from the generator's maximum capacity. Make sure to factor in the safety margin of 80%. This will give you the maximum additional load that can be safely added to the generator. Before adding any new loads to the generator, it is essential to consult with a qualified electrical engineer or technician. They can perform a thorough assessment of the system, verify the calculations, and ensure that the new loads are properly integrated without overloading the generator or compromising the electrical system's safety and reliability. Consider the power factor of the loads. The power factor is the ratio of real power in kilowatts to apparent power in kilovolt amps. It indicates how effectively the electrical power is being used. Loads with low power factors draw more current than loads with high power factors for the same amount of real power. If the loads have low power factors, the generator may need to be oversized to accommodate the increased current draw. This is especially important when dealing with inductive loads such as motors. Electrical codes and standards provide guidelines and regulations for electrical installations and generator sizing. Consult the applicable codes and standards such as the National Electrical Code or NEC to ensure that the installation meets all safety requirements. Consider NEC Section 220.3 for branch circuit, feeder, and service calculations. Understanding and adhering to these codes is paramount for a safe and compliant installation. Emergency generators are designed to provide power during outages, and their reliability is crucial. Regular maintenance and testing are essential to ensure that the generator is always ready to operate when needed. Follow the manufacturer's recommendations for maintenance schedules and procedures. Perform regular load tests to verify that the generator can handle the expected load. Keep detailed records of all maintenance and testing activities. Surge protection is essential to protect sensitive electronic equipment from voltage spikes and surges. Install surge protection devices at the generator output and at the distribution panels to mitigate the risk of damage from surges. Proper grounding is critical for electrical safety. Ensure that the generator and all connected equipment are properly grounded according to the applicable electrical codes and standards. Grounding provides a path for fault currents to flow back to the source, helping to trip circuit breakers and prevent electrical shock hazards. Automatic transfer switches or ATS are used to automatically switch between the utility power and the generator power during an outage. The ATS should be properly sized and maintained to ensure reliable operation. Regularly inspect the ATS to verify that it is functioning correctly. A single line diagram is a simplified representation of the electrical system, showing the major components and their interconnections. Create a single line diagram of the generator system, including the generator, ATS, distribution panels, and loads. This diagram can be useful for troubleshooting and maintenance. Document all calculations, measurements, and assumptions used in the load assessment. Keep this documentation readily available for future reference and for use by other electrical professionals. Accurate documentation is essential for maintaining a safe and reliable electrical system. Remember that working with electrical systems can be dangerous. Always follow safe work practices and wear appropriate personal protective equipment or PPE, such as gloves and safety glasses. If you are not qualified to work on electrical systems, consult with a licensed electrician or electrical engineer. Safe practices and understanding is important when it comes to electrical work. Consider the impact of harmonics on the generator. Harmonics are distortions in the voltage and current waveforms that can be caused by nonlinear loads such as electronic devices and variable frequency drives. Harmonics can cause overheating, equipment malfunction, and reduce generator efficiency. If harmonics are present, consider using harmonic filters to mitigate their effects. Reactive power is the power that is required to establish and maintain magnetic fields in inductive devices such as motors and transformers. Reactive power does not perform any useful work, but it does contribute to the overall current flow in the system. If the loads have a high reactive power demand, the generator may need to be oversized to accommodate the increased current draw. Power factor correction can be used to reduce the reactive power demand and improve the overall efficiency of the system. When adding new loads to the generator, consider the starting current of motors and other inductive devices. The starting current can be several times higher than the running current. The generator must be able to supply this starting current without excessive voltage dip or stalling. Soft starters or variable frequency drives can be used to reduce the starting current of motors. Load shedding is a technique that can be used to reduce the load in the generator during an overload condition. Load shedding involves automatically disconnecting non-essential loads to prevent the generator from stalling. Load shedding systems can be programmed to prioritize essential loads and disconnect non-essential loads in a predetermined sequence. Paralleling generators can increase the capacity and redundancy of the power system. When generators are paralleled, they share the load and provide backup power in case one generator fails. Paralleling generators requires careful coordination and control to ensure stable operation. Conduct a thorough arc flash hazard analysis to determine the potential arc flash hazards in the generator system. Arc flash is a dangerous electrical explosion that can occur when there is a fault in the electrical system. The arc flash hazard analysis will determine the required personal protective equipment or PPE for working on the generator system. Ensure that the generator is properly ventilated to prevent overheating. The generator should be located in a well-ventilated area with adequate airflow. Check the generator's cooling system regularly to ensure that it is functioning properly. Consider the noise level of the generator. Generators can be noisy, especially when they are running at full load. If noise is a concern, consider using a sound attenuating enclosure to reduce the noise level. Ensure that the generator is protected from the elements. The generator should be located in a weatherproof enclosure to protect it from rain, snow, and other weather conditions. The enclosure should also be designed to prevent unauthorized access. Consider the fuel supply for the generator. The generator requires a reliable fuel supply to operate during an outage. The fuel tank should be properly sized to provide an adequate run time. The fuel should be stored in a safe and secure location. Inspect the generator regularly for any signs of damage or wear. Check the wiring, connections, and components for any loose or corroded parts. Repair or replace any damaged parts promptly. Keep the generator clean and free of debris. Dirt and debris can accumulate on the generator and cause it to overheat or malfunction. Clean the generator regularly with a soft brush or cloth. Regularly check the generator's oil level and coolant level. Add oil or coolant as needed to maintain the proper levels. Follow the manufacturer's recommendations for oil and coolant changes. Check the generator's battery regularly. The battery is essential for starting the generator. Ensure that the battery is fully charged and in good condition. Replace the battery if it is weak or damaged. Perform regular load tests on the generator. Load tests verify that the generator can handle the expected load. Perform load tests at least annually or more frequently if recommended by the manufacturer. Keep detailed records of all maintenance, testing, and repairs performed on the generator. These records can be useful for troubleshooting and for tracking the generator's performance over time. Consult with a qualified electrical engineer or technician for any questions or concerns about the generator system. Electrical systems can be dangerous, and it is important to have a qualified professional perform any work on the system. When adding additional loads, consider the future needs of the facility. Plan for future growth and expansion when sizing the generator and the electrical system. It is often more cost-effective to install a larger generator than is currently needed than to replace a smaller generator later. Consider the environmental impact of the generator. Generators can produce emissions that can contribute to air pollution. Choose a generator that meets the applicable environmental regulations. Consider using alternative fuels such as natural gas or propane, which can reduce emissions. Explore the possibility of using renewable energy sources such as solar power to supplement the generator. Renewable energy sources can reduce the reliance on the generator and lower operating costs. Be sure to install carbon monoxide detectors if the generator is indoors, and to follow all local, state, and federal codes regarding generator use and safety. When sizing a generator, also consider the voltage drop that will occur when the generator is loaded. Voltage drop is the reduction in voltage that occurs when current flows through a conductor. Excessive voltage drop can cause equipment to malfunction. Use appropriately sized conductors to minimize voltage drop. Consider using voltage regulators to maintain a stable voltage level. Ensure that the generator is properly synchronized with the utility grid before transferring the load. Synchronization is the process of matching the voltage, frequency, and phase of the generator to the utility grid. Improper synchronization can cause damage to the generator and the utility grid. Use automatic synchronizing equipment to ensure proper synchronization. Consider the use of a supervisory control and data acquisition system, or SCADA, to monitor and control the generator system. A SCADA system can provide real-time information about the generator's performance, including voltage, current, power, and fuel level. A SCADA system can also be used to remotely control the generator and perform load shedding. In addition to the above considerations, it is also important to ensure that the generator is properly permitted and inspected by the local authorities. Contact the local building department to determine the permitting requirements for generators. Schedule an inspection of the generator system after it is installed to ensure that it meets all applicable codes and regulations. Consider providing training to the facility staff on the proper operation and maintenance of the generator system. Training can help to prevent accidents and ensure that the generator is operated safely and efficiently. Keep a supply of spare parts on hand for the generator. This will allow you to quickly repair the generator in the event of a breakdown. Consult the manufacturer's recommendations for the recommended spare parts. Establish a written emergency plan for power outages. The emergency plan should outline the procedures for starting the generator, transferring the load, and shutting down the generator. The emergency plan should be reviewed and updated regularly. Communicate with the local utility company about the generator system. The utility company may have specific requirements for generators that are connected to the grid. It is important to coordinate with the utility company to ensure that the generator system is properly integrated with the grid. Regularly review and update the generator system to ensure that it meets the changing needs of the facility. As the facility grows and changes, the generator system may need to be upgraded to provide sufficient power and reliability. By following these guidelines, you can ensure that the emergency generator system is properly sized, installed, and maintained, providing reliable power during outages and protecting critical equipment and processes. In conclusion, assessing additional loads for an emergency generator requires careful consideration of various factors. Accurately measure existing loads, calculate total load demand, account for power factor and motor starting currents, and verify generator capacity. Always prioritize safety and compliance with electrical codes. Consulting with qualified professionals ensures a reliable and safe electrical system.